Hello, y'all. Barely we're doing it back for an extra video. So I'm going to do some classical mechanics problems, graduate level. Basically, going to go through some of the problems that we're doing and see what y'all think. And you know, problems that I went through. I think the solutions are pretty nice. Think y'all enjoy it. Y'all be able to tell me what you think. I'll also be checking my compiled rates from time to time, perhaps. But I think my solutions look pretty good. And we'll go ahead and get started. So, and what I'll do, my pad is going to be sort of long-wise, and I'll have the textbook out as well, so you can see the problems that we'll be looking at. So I'll start with problem 7, which is this one right there, which is basically going to be showing uh, the Lagrange equation can be calculated in a different way. And I'll actually go through the derivation as well, the first part of it, the early part of it, so you can see how we get to this point. Even though it's not necessary to do this problem, but the derivation will put into perspective some of the things that we'll do later and make it make sense a bit more clearly. And so we're doing some graduate level mechanics. Boom. All right, so we'll get started. So the idea is to look at the Lagrange equation so that we can make a sort of change, and our solution could look like this for the Lagrange equation. Now, the Lagrange equation is an equation that allows us to solve more complicated um, mechanics problems uh, while lessening the amount of degrees of freedom that we have to calculate to find a solution. So basically, it's a way of simplifying what we're doing to make it easier to solve. So what I'll do is I'll start with the Lagrange equation. I'll explain it a bit as I go along. And if anyone pops up in the live, you'll let me know if you have any questions, and I'll answer any questions that come up. And but until then, we'll just keep it rocking. So we'll call this, and we're using Goldstein, by the way. You also saw the title of the book on the intro. So it's a graduate level textbook that I like the book. I think it's a pretty good book so far. I mean, it's not, it takes a while to get used to textbooks. At least it took a while for me to get used to textbooks. But of course, now I've been reading textbooks for years and getting used to reading them. At first, they seem like sort of a foreign language, and to a certain extent, they are, because physics has its own way of wording things and it's peculiar language that is, of course, English, but it's specific to the task at hand. I actually looked at a video on classical mechanics from a foreign university. I think it's in Netherlands. Professor's very good. Helped me with my understanding. And I hope this will help you all. And but he used English, and he said because of the specialized language that apparently a lot of the specialized language is in English. Move this real fast. So and again, we're taking the Lagrange equation and we're going to show it in a different form. So, and actually, thinking about it, no, I'll go ahead and go through it. So, The first thing to know when we're talking about Lagrange equations, and I talked about this a little bit last week on Saturday, we have something called generalized coordinates, where it allows us to, as I said earlier, reduce the amount of degrees of freedom that is necessary to describe a system. If you see me looking to the side, I'm just looking at my notes there. And perhaps I like to look and make sure that the screen is functioning properly, but perhaps I'll just tab over to it every now and then to make sure it's looking all right. And make sure to drop a line if you drop in. Ask any questions, make any comments. So if you have a coordinate, let's say you have so many particles, your regular coordinates, I'll just call them chords, might be like this. And I'll use a bold for a vector. So if you see a bold like this means that that is a vector. So for instance, R1, R2, and up to Rn. So that's what I mean when I write in a letter in bold, it's a vector. So you might have R1 and R2 and so on and so forth. And those are all just coordinates for, let's say, each particle. You know, you have a field of particles like stars in the universe. You know, I'm into astronomy. The position of that particle might be R1, and each of these particles will have their respective R value all the way up to Rn, which is a vector that's letting us know the position of that particle, right? What we do with generalized coordinates is we look at the degrees of freedom of the system, and we find ways to decrease those numbers of degrees of freedom. And the symbol that's utilized to denote that is the Q symbol. So instead of just having R1 by itself, we would have R1 and would have Q1, Q2, Q3, all the way to, now this one is a bit different, Q3N minus K and T. So the 3N minus K is the degrees of freedom remaining after we reduce the degrees of freedom. I'll start calling that DOF. And the K will be the constraints on the system, which is how we reduce the degrees of freedom. So if you have a common example that's used in class is if you have a container like a balloon and it has air in it, the air is contained within the container, so that causes a constraint that limits the degrees of freedom of the air. You know, it could only go so far, as an example. We didn't do a problem like that because it seems pretty complicated as far as all the different particles to calculate things like that. But it does give the idea that there's a constraint on what the particles can do. Later, I'll do a problem like a pendulum that's constrained by the bar that's holding the pendulum in place, and it's constrained to go in a plane, to swing within the area of a plane. So we'll look at how those constraints play out. So right now it's very theoretical and conceptual, but when we do problems later, we'll look at it in more detail. Now, the way that we get to the Lagrangian is we take a system in motion, which means, you know, and right now we're doing classical mechanics, so we're dealing with Newton's equations. So we would have F equals ma, of course, except now we're dealing with a system of particles. So each of these particles would have their own, you know, forces acting on them. Another thing we'll do is recognize that acceleration is the derivative of velocity, and we'll recognize that m times v is momentum. So we're going to be momentum, the derivative of momentum, because the derivative is being taken of velocity. So this denotes that we're doing a system with motion. There's also a version that deals with static, doesn't deal with motion, which confused me at first because they sort of do the same calculation, but change the fact. It seems like the same thing, but they start changing things. But I realized after learning in class and watching my video, that foreign video I was telling you about, that with the static particle, the static system, they don't use F equals ma, and with the system in motion, they bring in F equals ma. And what we end up doing with this is we subtract and we have this equality. So we'll basically utilize the fact that the force that's being applied to the system that's causing it to move, that's giving it acceleration, minus the time derivative of the momentum of the system equals 0. So basically it's just subtracted F equals ma. Now, I had mentioned earlier that the forces at play, the constraints, like for instance, the container that's holding air, limits the degrees of freedom. So, the balloon that's holding the air in, there's pressure keeping that air in. So we have Fi is going to be divided into or broken into the F that's applied to the system from outside plus the F of constraint, whatever that constraint is. And what we'll do is apply this formulation to work to get us to the Lagrangian. So work, which you may know, in the context of Newtonian, is going to be force that's applied on a particle, dot product it with the distance that the particle moves under that force of work. One thing that we do different is we define a sort of virtual movement where it's similar to the dx, but imagine a movement that's so very small that it doesn't even register. It's so small that the dynamics of the system don't really change. And what I'm going to do here is plug in our equation earlier, because since this equals 0, if we plug in this, it still equals 0. And this is how I think about it. So some of the explanations might not be the most advanced yet. This is how my professor might explain it, but hopefully you all get the picture. And we could also recall from earlier that we broke force up into the applied and constraint. So now I have Fi minus momentum I. Oh, hold up. Applied plus F constraint. So I just wrote it out earlier, but that's applied and constraint from before. Minus the time derivative of momentum. Dot product it with the virtual movement. Equals 0. Now, the thing about dot products is we can distribute this outward. So this is the same thing as the dot product of force times this plus the dot product of this plus the dot product of that. So you could distribute this out and have 3 different dot products. What we do is we recognize that the constraint, since, like, let's say if I have a balloon and if the particle is, moving along without hitting it, then, there's no force. The idea, as I understand it, is even if the particle hits like this, the constraint force is basically perpendicular. That's keeping that in. So we know that the dot product of things that are 90 degrees away from each other is 0. So what that means is that the force of constraint dot product is going to be perpendicular to this. So it'll end up being 0. So if I were to write that out, I can group it like this. Right? And we're going to discard the uh, constraint one. So now we have this. And in the book, this is equation 1.45. And another thing as well, I notice I left off my summation. So let me add that here. So to get the net, basically, we add them up amongst all the particles. So we have this. And what we'll do here, we'll actually break this into 2 different integrals. Right. Field equals 0. So what we have is we have 1, and we have 2 as far as different components that we'll solve to end up to our final answer. Now, the first one is end up being pretty quick. So we have the component, the summation integral f I a dot integral r I. And one thing that happens is this can be broken up into its component parts. So essentially what we have is, remember that R has its separate components. Q1, Q2, and so forth to Qn and T. And what we can do is actually uh, extrapolate the derivative of this R, and it'll look something like this. Ri equals, so this is going to be basically a chain rule. We have partial derivative of Ri over partial Q1. Then we have Q partial Q1 over partial C. Uh, we have partial Ri, and this is a plus, over partial Q2, partial Q2 over partial T. And I'm not remembering clearly if this is over T. This might be over something else. I have to think about that. But suffice it to say, this keeps going. I don't remember if that one is over T or not. I know that it reduces to, I was to make some more space here. This reduces to, like it continues going out. This reduces to a summation I and partial R I over partial Q J. And the idea is that each of these series of numbers, however many we have, we're going to just call that J and sum over them with the summation. And this item here, I don't remember if it's by dt, but I could tell you that it resolves into Qj. So basically, we could substitute this. So this is basically an aside. I'll make this in blue. So this equals, you sum ij partial ri over partial qj. Qj, and this is going to be still dot producted with f I a. We have that. Another thing that it seems you just have to just remember is that this summation and dot product, and I'll just write this out in blue as well, the summation I of f I a dot producted with partial q j, and there's an I here. This just equals something called qj. So I guess it's just a way to simplify the formula or equation. So that means that what we can do is we extracted the I summation, because of course this part here is only on the j, and now the q is on the j. We have the summation of qj and the virtual movement of qj. So that's that part, the part one figured out or resolved. Next thing we look at is part two. This part is a bit longer. Where we had summation I of the time derivative of momentum dot the virtual movement I. So all we're doing now is extrapolating this second part. This can be broken down further into its components. And we can say that mass I v dot I, and that's the same thing as I mi or double dot I dot producted with I. Now earlier we've already did this extrapolation of that component there. So I'm going to go ahead and just add it in again. We've already done it. Again, it's the extrapolation of that virtual component earlier. And now finally we get to, so now we have two R's here, which is what we're heading to. If I extrapolate one more time, I'll call this d of dt. All right, so we have this. So all I did was take my velocity and extrapolate it into its derivative components, insert the extrapolation of the virtual movement component from earlier, and now I have this. So one thing that happens is we can actually take the derivative of this. We can actually extrapolate this out, and not the whole thing really, but if I was to take this part here, and instead of having the derivative on just the r, if I put the derivative on the entire thing, so if I had d over dt, and instead I have some ij mi r I dot producted with partial r I over partial qj. Now we actually work this out with our what do you call it, chain rule and everything that we have to do. um, we will end up with some ij. I'm going to first take the derivative of the first part. Mi is a constant. So it would be d over dt times this I first. And it's still dot producted with ri over qj. Plus, now I got to dot product the second half of this. So it'll be some ij. And actually, the sum on the outside can cover both of these. So it'll still be some ij, m, or I, because again, now I'm taking the dot product of the second part. Give me the derivative of the second part. So it's d of dt on the second part, partial ri over partial qj. And this is all in the summation. So if we look at this, we notice that this part here is the exact same as this. So if we put the derivative on the outside, we get the same thing back plus something else. So I want to substitute for this. I can subtract the additional thing, and I can have summation mi d over dt r. Oh, looks like the had an issue. Let me get it loaded again. All right, there we go. So we have r. Right now I'm solving for this by subtracting this to the other side. I dot and dot product partial r I over partial q j. I'm mistaken, made this a I equals d over dt. And I'll actually put the, well, I mean, that's still fine. ij mi dot I dot partial r I over partial q j minus m r I dot partial r I q j. And we still have our summation, which are left off on this side. So that's still sum ij over the whole thing. So we can see that I can replace this with those two things. And that's what I'm going to do. I'm going to replace that thing with those two things. And what I'll do is actually just color it black to show that I've actually input it back into the live calculation. So we have that. And actually, technically I can't do that because I have to add the in part, but I could just copy it instead of writing it over. So we have this. And also, so plugging it back in, we have to add the element back at the end. And now we have this. Another thing we can look at is this partial derivative here. We can swap partials there. So that's going to end up making this equals. And I'll save a bit of time by copying all of this down. Just a few things. So what I'll do, I'll call this partial qj, and I'll put the d of dt there. So all I did was just swap those two. And I left off my dot on the R. Did that one mistake. Left it off on this one too, looks like. That's the only thing about when you write things a few times. Sometimes you might drop a component somewhere. And what I'll also do while I do this is just call this V. Right? So that's a dot product. And I'll do the same thing here. I'll just call this R dot V. And we have that. And there's one more V I can do. That's a d of dt right there. And I'll actually just copy this down one more time. And this entire thing ends up being a V. So this dr(i)dt. So I will just call this partial of V. So this dr(dt), I called it V, and just put it up next to the, what's inside the partial. This R dot here is a V. This R dot here is a V. And now we have this. I'm going to check my notes here. Looks like it's going all right so far. Now, one thing about this line, this part here, is that if I take a derivative of the top and the bottom, it's fine. So if I was to change this R dot, into this R into R dot, which is V, all I have to do is change this Q to Q dot. So I'm going to turn the R into R dot and the Q into Q dot. Basically, is the DTs cancel, And thus, you know, I didn't change the value of anything. I just changed how it looks. And now we have this. Um, Another thing that we can recognize is, and I won't write this one out in detail, is that the dot products that we have, the dot products here and the dot products here, they end up extrapolating out as kinetic energy, as mv squared. So I guess you can say if we were to take the derivative of mv squared, so I guess if I was to put it simply, we can say that v squared equals v dot v. That's just one way of writing it. And we see a v dot v there, so we can go ahead and make that a v squared. And another thing that happens as well is and I'm not totally clear on the half, but a half pops out of that. I've asked my professor about that one. I don't remember the details of that one. But I guess we can say that if you have this dot product with these, in a sense, 1/2 v squared is that. But again, this square I'm going to have to look into a bit. Suffice it to say, I can expand this one more time and call it d dt. And I already have the summation for that on the outside, so I can remove that summation. This partial q here, I can move it to the outside. So we have partial q dot, that's with j, and 1/2, still we have our in there, v squared, minus, we have the same thing there. I can extract this q, this partial q out, qj, 1/2 mi v squared. All of this is still in brackets, and then we still have our q j at the end. So we have that. And something else we can do here, it's like I just rewrote a line and move the summation. So the I is basically only here. So what I can do is I'll just copy this here to save a few seconds. And now I'll just make a little bit of space here. And instead of this being ij, I'll just make that j. I'll put the summation for the I here, because that's the only thing on I right now. And now we have that. And again, we know that's the kinetic energy. So I'll go ahead and plug that in, and I'll write it out this time. So we have sum j d over dt, partial, and this whole thing is t. So I'll just say partial t over partial qj dot minus partial t over partial qj and partial qj. So now we have our whole thing here. Now, the last thing that we have to do is simply put these two things together. So remember that we were working on 1 and 2. We had 1 minus 2. So 1 was the summation, was it I, or the summation j, qj, and squiggly j, qj, squiggly qj, the little delta signal. And remember that this was subtracted to 1 and 2. So I'm going to just plug what that was. And I'll just copy this one down so that one is right there. Now we put our 1 and 2 back together. We can further simplify this by combining the summations, since both of them are summed over j. I can do like that. And we can further simplify this by distributing the negative. So the negative here will be distributed over everything. So if I was to copy this down and distribute the negative, basically I would have minus this, and I would have plus that. You can see how that goes. And by the way, all of this still equals 0. And now the way this works is, in order for this to equal 0, I could also remove the extra squiggly, since they're both being this is being applied to both the same. So I have this. And the way for this to equal 0 is each component here must equal 0, since they're, this one is not being having a derivative. This is a derivative dot. This is a derivative q. The way I think about it is they're being either no derivative or derived by different things. So each of these components has to equal 0. So that means that if each of them equals 0, the whole thing equals 0. So I can set this equal to 0 if I bring my q to the other side. I can have this. So I'm going to subtract q from both sides, end up with q over here. And there's a negative on the q over here. And if I multiply everything by -1, I have a positive here, a negative there, a positive there, and we look like that. Now, this is actually one step removed from the Lagrangian. What I can do here is I can basically input potential, and it's an extra step that we don't need here. But we're almost at the full Lagrangian equation. Just remember that the Lagrangian is T minus V. So if I insert a minus V to each of these, recognizing that if I have, let's say, well, I'll get to that. I'll need to look at it to explain it clearly. But suffice it to say, we could add a potential to a system, and if we take a derivative of that, the potential is a scalar, so it'll go away. So you can add or subtract the potential without changing the actual physics. So in short, I can just minus v to all of that, and then that becomes a Lagrangian, and this is how we'll end up solving products later. So keep this part of the equation in mind. But what we'll do is solving the problem. Remember the problem said, bring it up again. We're showing that Lagrange's form could be like that. So the way this is done is we basically take a crazy derivative of that first term. So basically I'm going to take the derivative of this, I'm going to derive it out. I need to show after I take the derivative that it equals, and let me move the book over a little bit. I need to show after I take the derivative that it pops out the same thing plus an extra negative partial t over partial qj. So that way we can, show the proof that we need to show. So one thing to keep in mind is that, and actually I'll keep it in the main, dt of partial t over partial qj dot and t equals q of t, that's important, q dot of t and t. Those are the components in the generalized coordinate space that we derive from here. Stands for, I thought I wrote that down. Yeah, right here. So in the space of the general, we reduce the degrees of freedom by q. P is a function of those terms. So we have to keep that in mind when we do our derivatives. And here we go. So I'm going to start with, I'll just call this, so first thing we can do is we can actually swap these. So we mentioned earlier how we can swap the partials like this first. And that's going to equal partial q dot of partial t, and all of these have a j, forgot about j, partial t over partial qj, and dqj over dt. So this is definitely with respect to t, since we have a t there, and each of those are um, um, functions of t. We have partial t over partial q dot j and partial q dot j over dt. And then we have partial t over partial t and dt over dt. So this is how this extrapolates out. We know that this is just equal to 1. You can simplify this a bit farther. I'll copy it down. So since this is equal to 1, let's delete this out. We have this dqj over dt. That's qj dot. This one is qj double dot. Now we have this. And now we have the last derivative, which is which can get a bit complicated. So what will happen is this will distribute first of all. And make this a bit more amenable. So what I'll do is actually make some space to distribute this out. This here. There. Also go there. This. So just distributing those out. And each of these will have their own derivatives out. Now, it is a being very ugly derivative. I see we're already at the bottom of the hour. If you really want to see the derivatives, you can let me know. But suffice it to say that when we actually extrapolate these derivatives out, we end up getting a whole bunch of ugly stuff, and we do end up getting an extra thing that we need. So remember, looking at the book, we need to get, this looks just like the equation that we had before. So we scroll back up to the equation that we had before, and I'll highlight yellow. We need that same equation, but we need 2 of these, and we could just, plop this over and make that T dot. So that's in the book. So I can just plot this over and make that T dot. But when I actually take this full derivative with this partial Q dot, it needs to go ahead and pop out another one, and it does that. So with actually extrapolating these derivatives out, we find out that we get that, and we did prove the problem. So that's that. Just some good derivatives. It took longer than expected, but I explained a lot of details that's going on. And perhaps what I'll do tomorrow, because I'll still have the regular show tomorrow at 8 o'clock, I might come in, either do some more graduate, or I have some undergraduate problems to do in my review course. Yeah, several things I could apply. So, and also have some pretty cool problems that I did. So that's what I might do. Undergraduate physics problems that I did to prepare for the exam that we had. Many things, many choices. Those who watch, you could always drop a line. You could see the post page on the YouTube channel. It says like comment. Let's see what the actual word is. It's posts. So I believe you should be able to make a post there. People have commented there before, if I recall. Uh, Maybe I'll put a poll there. You can let me know what y'all would like for me to cover tomorrow. That's what I'll do. I'll put a nice poll there. Y'all can let me know. And or you can comment on the video, so on and so forth. I'll be sure to be more consistent with the posts, with the videos. You can let me know what y'all think. And I'll see y'all tomorrow. Have a good night.